microphone pull-up.
Just a second.
And we have an exciting,
Some feedback audio here.
topic for you today.
Yeah, I hear some feedback.
And yeah,
okay. I think we can proceed.
Yeah, perfect. Yeah, so for everybody who's not familiar with AVL, we are a very research-focused company, 75 years. We do engineering consulting. We make our own simulation software, and we also make our own test equipment. And we work with customers all across the globe. Here are some of them. You will be able to meet them, and some of them also, some of our partners and customers at our mobility conference that is happening next week in Norway and Michigan. Panel discussion will be how automotive will change in the face of AI. We will have Hexagon and Microsoft on the panel, and we'll discuss with them. On the next slide, you will find a quick registration link if you're in the area. We are more than happy to meet you there in person. But to go right into the agenda of today, we have an exciting topic about how to optimize a gearbox to reduce noise levels, and give you a quick motivation, technical background, and then really the core of today's topic is optimization. And Michael is actually an optimization expert, has worked many years in the industry on optimization topics. So this is what we do today.
Yep, this is a very high impact, I'd say, workflow and methodology that the industry is leaning towards very heavily. So we'll jump right into the motivation here. Comments?
So with conventional ICEs, the motor, the engine is really masking a lot of noise from the gearbox. So with EVs, the e-motor is actually very quiet, and nothing hides really annoying noises from the gearboxes anymore. So this gets annoying, and we want to prevent it. And also it's a cost topic. In order to produce cheaper gearboxes that are still acceptable to the ear when you are driving at low speeds, the optimization of the gearbox is of much more of an importance than it used to be. And if we move on, the gearbox that we will be looking at today, we have a screenshot here. In the middle, we see the e-motor that is connected to a planetary transmission, and then it goes in 2 gear stages all the way down to the differential, which brings the power to the wheels. And we see a section cut down here on the right side. You see the bearings, the meshes, and the taped roller bearings on the differential. And actually, these screenshots or images that you see here are from our tool AVL Excite, which is a multi-body simulation tool. And basically all the elements you see here are modeled in one 3D model, and it lets us simulate the interactions of the vibration of the entire part. Now, the focus of the optimization today is specifically this second spur gear stage. And we will see in more detail on the technical background on the next slide. So where does the noise really come from, or how is it introduced? When we look at this gear, it's the point of contact basically by rotating and with the teeth, it introduces stiffness across the rotation. So this rolling contact of the flanks and the change of stiffness is introducing vibrations into the system. And these vibrations excite and transfer through the bearings and the shafts onto the case, to the surface of the case. And we can follow this on the transfer path into the housing. So actually a nice technology in Excite lets you analyze this transfer path. So when we look here on the gear, we see the transfer path analysis, and specifically we can pick a point and see the connected elements and identify which connected parts contribute most to the to the actual vibrations. And by that, we can identify really what part is causing the majority chunk of the vibration. In this case, it was identified as the second spur gear stage, and we will look at specifically this one today. It's worth mentioning that AVL Excite works on the time domain, so we can run fully transient ramp up over the entire RPM range over time. And what we can do then is draw a diagram about on the full scale of the point. So on the right side we see the case, and we pick actually a sensor point on top of the housing. And looking at this point, we can identify, okay, which one is the causing part or has most promising part for optimization. And this is what we look on the next slide.
Oh,
and
yeah. So
okay, yeah, I hand it over to you. With
yeah.
this one, basically, we need to know what we want to optimize and what we can optimize, and this is exactly where your specialty is coming into play.
Yeah, for sure. Thanks for the overview on gearbox design and engineering. So, yeah, for optimization, you'll always need some parameters that you're varying and then some KPIs that you're looking at. And so for this type of study, we decided to look at the response mean, which is considered basically the average sum of all the orders of the first four excitations of the second gear stage. So that's represented by this orange line. And then the other things we were looking at was the first harmonic order max, the maximum of that. So that's this red line. And then the blue line is the second order harmonic max. So we didn't care too much about the third and fourth because that was already incorporated into the mean of the global, the first KPI. And then the things we're varying is the tip relief within the gear, the lead crowning in the gear, and then the helix angle correction in the gear. And these are basically drawings over here that show kind of how that looks relative to the gear design. So we're basically doing the tip here. We're going to do the lead crowning, which is this more width-based parameter, and then the helix angle correction, which is sort of a twist-based parameter here. And then when we go to the next slide, I'm going to talk really about how we're going to perform this optimization with Excite. So you can see here that there's Excite here on the right side, and then on the left side is our optimization tool known as CAMEO. And what basically happens is CAMEO varies the parameters in Excite, and then Excite calculates the KPIs out of that and sends it back to the optimization tool. And there's like a circular feedback that occurs here. This whole workflow can be run on Windows or Linux clusters because, as you all know, optimization is quite computationally intense. So this is something that, it shouldn't be too much of an issue. And just for the calculation's sake, each simulation of point that we do takes about 10 to 15 minutes or so. And I'll explain why that's important later on in this presentation. So we're attempting to build out a design of experiments, which is the first step of any optimization workflow. And these are the boundaries, the min and max, the range effectively of the variation of these inputs that we're doing. So tip relief is 0 to 15 micrometers. Same thing with the lead crowning. The helix angle is negative 15 to 15 micrometers relative to a certain point on the gear. And then we also had to vary the speed from 3 to 21,000 RPM because we wanted to understand the sound output over speed range. And then, like I said earlier, our KPIs is the first, second harmonic of the gear, meshing frequency, the maximum of that, and then the next one will be the sum. So it's basically 3 outputs and 4 inputs that we're varying. And then in here, you see the workflow of the active DOE. So like I mentioned, we're going to start with this reduced design just to sort of understand the initial design space. We've defined that we're attempting to minimize these KPIs And then during this simulation or test, as we would call it, the results are being sent to this active DOE. And what it's doing is it's effectively using a surface. It's developing like a response surface off of these inputs that's sort of guided by our target. And then it keeps on like telling it, hey, maybe you should fill more points here, maybe you should fill more points there. So it's effectively a space filling algorithm with a bit of enhancement on AVL's own IP. And then what you'll do here is look at your results and see if there's enough. And then there's an offline optimization that will occur here using sort of a hybrid of genetic algorithm and gradient-based methods. So when we go into the DOE, you can see here that we filled the space quite well. It's not a full factorial. As you can see, there's some gaps that are here. And the reason why is because a full factorial would take over 50,000 designs to be fully filled. And you can imagine at 10 to 15 minutes, those 50,000 designs could take months to actually compute, depending on your computational resources. We did only 900 here, so you're only really looking at 900 points. And those 900 points are took us probably about the weekend to do. Went from Friday roughly to Monday. And that's the real power of having an intelligent space filling algorithm like the active DOE. And then in the design of experiments here, after we've done all of that, what we're attempting to do is to create a meta model or regression model of our DOE values. So we used a neural network to represent the simulations that we had, and attempted to make an accurate representation of our different KPIs. So you could see here we have the first harmonic on the top left plot, and on the top right we have the second harmonic, and on the bottom we have the sum of all the harmonics. And what you can see is there's a relatively good correlation. We have different metrics, R squared, RMSE, and RMSE. And they all are relatively good. You're above 95.95 for all the R squared. So it reflects a relatively accurate surface of the DOE that we were doing. And then in this thing that we're doing here is we took a slice of that surface. So this is what we call an intersection or cut of that surface. And what we're doing is we're varying individually the inputs to understand the outputs. So it might be a little bit blurry here. Oh no, actually that looks perfectly good. So you see here we're varying the inputs, the CAA opt, CB opt, and CHB opt. These were those three inputs of the gear tooth that I was talking about. And we're varying those individually to understand how the surface moves, because when you vary one, you move in 2 dimensions across the other surface. So you see when one of these lines is moving, the other two, when one of these lines moves in the horizontal, the other 2 red lines are moving up and down. So this is just for you to explore and understand sort of how that's how your variation looks when you're doing these exploration. But we used an optimization algorithm to effectively arrive at an optimum. And what we did after you do that, because it's a meta model output, you want to ensure that what you've arrived at using the meta model or the neural net that we were training on the surface, you want to actually validate that with a simulation or a real test to ensure that that's exactly your real value. So this is where you see here on this picture, we said we verify it in Excite to ensure that that's real. This is the optimization. So this isn't the end of the presentation by any means, and I'll explain why in a bit, but this is effectively how the results look. In this plot here, we have the unmodified geometry sum of the orders, so you see it's quite large. And then we have the sum of the orders of the optimum, which is lower. And you can see the delta here was roughly 75 decibels lower at the max. And we have, you could say, roughly like a 40 decibel reduction across the entire speed range. So this is a successful optimization. However, there's a couple of questions we want to ask here, and we'll get to that in a bit. But this is how the geometry looks when you're looking at the unmodified geometry and the optimized geometry. So you see your stress at the teeth is not very well distributed, whereas in the optimized geometry, you have it very well distributed. So you basically have a more durable gear set as well as a gear set that's quieter. So, and then in this presentation, this portion, this is a useful portion because what this shows you is the sensitivity of which of the input variables, the variation parameters that we were defining earlier, which ones have a sensitivity to the output. So you could see here, like in the sum of the orders, you have this CB, which was the lead crowning, is the most sensitive to your harmonic output. And then the same thing is this speed is as well very, very sensitive. So as you're increasing or decreasing in speed, there seems to be a change in your decibel, which is in fact intuitive there. So this helps you to understand if you wanted to continue, you could probably reduce your input set because it's less important. It's less sensitive to your output. So something like this tip relief is probably not that sensitive to your harmonic output. And so maybe you could reduce that and focus more on the other parameters. So this is where the real question comes in the whole robustness portion of this material that I'm.
And
Oh, go
before
ahead,
you
Thomas.
jump into it, Michael, I just wanted to mention if there's any questions so far, you can put them in the comments. Put it on LinkedIn in the comments or on YouTube in the comments. We can try to answer them directly or follow up. And yeah, just also
Yeah.
I will post a link to our conference in a bit. But yeah, I think now is the really the exciting topic.
Yep. So we did an optimization, and now comes the question of manufacturing variability. So whenever you do an optimization and you're only really looking at the global optimum, it could be on a very steep hill. And if you deviate a little bit with your inputs, suddenly your performance drops off dramatically. It's not that you didn't find the optimum, you didn't find the most robust optimum. And so that's where inevitably in real life you'd have to maintain really tight manufacturing tolerances. Any slight variation will suddenly make your system perform way worse than probably the second best optimum. And so I'll show you guys a little bit about what I mean here. And you see some of these questions is, can it even be manufactured? So that's holding the tight tolerance. And how will the tolerances affect the decibel? So you can see here we have a little plot here that's showing the variation of the sum of orders. So we did a quick little tolerance study here, and we show there's a band of min and max sum of the orders, and then there's a delta between the two, and there's large deltas. So you have very varying performance at the maximum here. And the same thing goes for the first excitation. You can see at around 11,500 RPM, you'll have a huge variation in performance based off of your manufacturing tolerance. So this is something you want to take into account because you mitigate problems downstream. And we'll show you guys what we did here for that. So effectively the sum, the delta of the sum is 40 decibels. The delta of the sum of the min and max of the first order is 19 decibels, and we'll get that much lower. So this is effectively what I'm describing with when I was talking about surfaces. So the surfaces you can see here are of some of the outputs here of the first harmonic, second harmonic, and some of the responses. But we only have two inputs here, an X and a Y. In theory, you would have 3 or 4, but it's difficult to visualize. But effectively, what we're doing here is exploring that surface. And we will eventually come to an optimum that we calculate here. So let me just show you guys how that looks. So you see here, there's an optimum that was defined here based off of trying to balance the 3 goals here. I will allude to a problem here, and you can see the problem on these two, on the first harmonic and the second harmonic especially, that it's kind of on the side of a slope. So if we start varying anything, you'll get dramatic swings in that first harmonic and second harmonic output. And it's important to consider that. And I'll show you guys how we consider that right now here, which we do a robust optimization. So with this robust optimization, we're attempting to consider the tolerances. And the tolerances that we determined was just doing a 3 sigma of the sort of optimum that the optimum that we will look for. So effectively what it does is every time it says I find an optimum, it will then do this variation study. And we're attempting to minimize the distribution, of these first harmonic max, second harmonic max, and the response mean. And if there's a low variation in that output within our tolerance of the input, then we have what's considered a robust design. But if there's a large variation, then that means it's not a robust design, because any slight deviation of your input suddenly creates a wildly different performing system. So this is how we went about doing our robust optimization. So this is actually the final output of the robust optimization. And remember, I mentioned we were on the side of this slope over here, on this blue area for both the first harmonic and the second harmonic. And now we're not. So we're in a bit more of a flatter portion of this valley of the surface, and we didn't move very much compared to on the mean. So this was something where it's a more robust output, and you could see that pretty much visualized over here, where you're seeing the sensitivity analysis. So you're seeing we're kind of in a relatively flat area, a greenish area here, and you could see that there's not, given this variation, there won't be a lot of deviation of this surface. So basically this is like the flat area, the green. So we stay within the green. You can see these outputs over here, where we did another plot that I was showing you guys, where we showed the sum of the orders and the min and the max. And you can see here that the delta is a lot lower, and it's a lot more consistent as well here. Same situation here. It's especially low for many portions of the first excitation, but it's definitely, I would say as well, probably a lot flatter on the average overall than it was before. And you can see we have 24 decibel width of the min and max when we do that variation. So the smaller that value, the more consistently your system will behave, and you don't worry about any unanticipated noise. Same thing on the first harmonic. You see it's 14 decibel as the max, and that basically means it's a lot more consistent performing. And finally, you guys are probably wondering, okay, so you showed us the initial baseline, you showed us the optimum, and you showed us the robust optimum. And this is effectively the summary of all of that. So you could see here the red line is the unmodified, it's the baseline. And then the blue line is the sum of the harmonics of the optimum. And then the green line is what we did with the robust optimum. And you can see that it's not much different in terms of the actual sum of the orders, but on the variation, the robustness, when we vary those inputs a little bit, my green curve will look very similar to my green curve with all of that variation. Where if you just use the optimum and you did that input variation, your blue curve will look dramatically different. So it's harder to actually manufacture that. You have a risk that when you send that out and manufacture it for mass scale, you'll have two systems that'll behave quite differently. So yeah, effectively what we were doing here, just to summarize the workflow, was we defined our variables, we defined relative KPIs, we set up our optimization, and we performed model-based simulations. And then this is where you do the optimization of that surface. So you did the meta modeling of the surface, and you did the optimization of that surface, and then you verify it, which is what we were doing when we said send that optimum value back into the simulation tool to make sure your neural net and your simulation show the same value. And these are the benefits of it. You can do that for any system. We have workflows for batteries. We have workflows for fuel cells. You save a lot of time and money, and you actually are able to quantify your influence of the tolerance that you're setting. And that's one of the most important things, because we hear in industry a lot that people mostly work off of nominal geometry. And when it goes to production, it's never nominal. So that's something we take into account for a more robust system.
Yeah,
So,
ideally you want to, in the end, you want to be every vehicle exactly the same. So that's what you strive for. And
yep,
yeah, we can do the, as you mentioned, the same for e-motor. We probably do
battery.
battery, but specifically the noise of the e-motor is also a very similar topic.
Mhm. Yeah, and it's like you don't want as an OEM for your vehicle to be like, oh, I bought the Q1 2022 model and the Q3 2022 model is like the worst model because they had a tolerance drift at the factory. That's not a reputation you really want. So this is where you have consistency across your product, and that makes for a much better product.
Awesome.
Like,
Yeah, thank you so much, Michael, for this insight into the optimization topic. With that, we are at the end of today's Lunch and Learn. We hope to see some of you at the Reimagine Mobility conference next week. The link is in the LinkedIn comments. And yeah,
yep, we'll reconvene after the conference.
exactly. Next topic, probably battery after the conference in 2 weeks. Hope to see you again soon. Thank you
Yep.
and good afternoon.